Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my pleasure to introduce Radu Ho. He's a research director at INRIA, leading the perception group at INRIA Grenoble. And he has done a lot of work. Today he will show us two interesting pieces of work. And he has been IEEE 2001 program chair and also a lot of other editorial duties.
Okay. Thank you, Zhengyu. And thanks everybody for attending my talk. In fact, there will be two talks, two short talks. When I submitted a few suggestions to Zhengyu, he told me, you should present two instead of one. There will be more people. So I don't know if you came for the first talk or the second talk. Anyway, so the first talk will be will address the problem of audiovisual fusion, in particular detection and localization of what we may call 3D audiovisual, 3D AV objects, and using unsupervised clustering. And this work is mainly performed by Vasil, who is a PhD of Florence, who is here, and also other contributors. And let's see what we mean by audiovisual clustering. So what we'd like to address here is the problem of audiovisual perception in general. So what I mean by audiovisual perception in general is not necessarily reduced to, for instance, detecting speakers or detecting verbal speech or something like this related to and combining this with visual features, which is usually done. But we like to put this in a more general framework of, let's say, we call it computational audiovisual analysis. And we like to basically are interested into objects that are can be both seen and heard. So many objects around it can be both seen and heard. And I'm from a computer vision background. So when I started to do this, I thought, well, how could we put together visual data with auditory data? So it turns out that to start with, there is a intrinsically difficult problem because the two sensorial stimuli come into very different formats. And also, the main feature of vision is that it provides dense data. And the light sources themselves that produce, in fact, the light are completely not relevant for the task, because what you actually look at is objects that reflect the light. So it's reflections, in a way, that are relevant in vision. Although auditory is completely the other way around, because reflections of sound, it's really a problem, and what you really want to do is to detect acoustic sources. And auditory data is by nature a sparse information as opposed to vision. So our approach that in fact you can is described in two recent papers. So we decided to use binocular vision and binaural hearing, and to combine those two within the framework of 3D fusion. So the approach is based on finding the 3D location in space of AV objects. So what we propose is a generative probabilistic modeling, and which will at the end boil down to an EM algorithm, which in fact what we'll do will maximize the expected complete data log likelihood. So on one side there are, do you see this? Yeah. On one side, there is the observed data, which is the audio and the visual observations. And on the other side, is what is called the missing or the hidden data, which are the categories, the audiovisual objects that we would like to detect. So it's a completely unsupervised approach. We are not given the audiovisual objects in advance. So just to show you the kind of data that we process, so we about a year ago we put together database. In fact, you can access. I don't have internet access here, but anyway, this link goes to the KEVA, what we call KEVA dataset. So just to show you one sample of this dataset, it consists of synchronized stereo pairs, and the audio recording is done also with a binaural pair of microphones. Oops. So just to show you just to show you the kind of things that we have. So,
hello, my name is Heidi.
So there are two people that are actually visible and two other people that are on both ends of the table that are hidden. So they produce only auditory data. They don't produce visual data.
Yeah.
And sometimes two people speak at a time. Times only one person speaks, etc. Okay, so this is one example of things that we would like to process.
I know. Yeah, this is quite good. I think we don't have the reflection on the floor.
Okay, so it will go on like this. So I will show you in a while how we actually extract AV objects from this kind of scene. Okay, so just I would like to go very quickly through what we mean by binocular and binaural observations. But this is very straightforward. We process each image pair such that we can extract interest points, and then we match them. So this is classical epipolar geometry, some rectification, and then we have a number of 2D observations. So through a very simply minded matching technique, we provide, in fact, 3D observations in UVD space, where U and V is the location of a pixel, let's say, in the left image, and D is the disparity. So what you can see here is this. In fact, what I show here is the XYZ position associated with UVD. You can see there are roughly, these are the three speakers, this is the background, and these are some outliers produced by the stereo matching process. So I will call the visual observations F, F1, Fm, etc. And similarly, we have binaural observations. So what we use here is the interaural time difference. So this is just to show you how this is processed. So this is the left microphone, right microphone, and from this we get a correlogram, and then we detect ITDs. And then I will call so these are 1D observations, and then I will refer to these auditory observations as G, G1, GK, etc. And then our model is based on the fact that the generative model is based on the fact that both the audio and the visual observations are in fact a mapping from 3D space to the 1D space in auditory case and 3D space in the visual one. And so the function, so this function G, so S is the coordinates of a AV object out in the world, and so like it will be, for instance, a speaking person, and then the auditory observation GK are produced by this well-known function that is in fact simply the sound propagation in space, where SM1 and SM2 are the positions of the two microphones, and they are localized in the visual space. And similarly, we have the 3D visual disparities. So here I just copied classical things where the U, V, the D are given by this projective mapping, where B is the distance between the two cameras. And this corresponds to a rectified camera pair, but it can generalize to any other camera configuration. And with this, in fact, the auditory and visual data are put on an equal footing. We do not privilege any of the two modalities. And you may notice also that this is very useful to calibrate the camera microphone setup, because if you know, for instance, the location of acoustic source S, then the unknowns become SM1 and SM2, and then you can very easily estimate the positions of the microphones in camera space, and this is what, in fact, what we did. Okay, so now we have a multiple speaker model. So the parameters, unknown parameters of the system, of the method, are the speakers' positions. So they can be arbitrary number n of speakers. And then, because we do not know the categories, we do not know to which category each observation belongs, then we have to introduce assignment variables, which are the hidden data I mentioned before. So I will refer, A are the hidden variables for the video part, and A prime are the hidden variables for the, or the assignment variables for the audio part. And then this is a classical notation that it means that when, for instance, variable AM equal to N, it means that the visual observation M is assigned to speaker N, but also we introduce an outlier class N+1. And we have exactly similar thing for the auditory part. And and then the likelihood model that we use is also quite classical. We consider a Gaussian model for the likelihood of an observation to belong to a speaker, whether it is a visual observation or auditory observation. We also tried to use the T distribution, and in fact the methodology that we present is completely independent of the choice of the normal or the T distribution. And also we added an outlier model. So this is a uniform distribution that is a non-parametric, as opposed to the Gaussian or to the T distribution. The uniform component in the mixture model is, in our case, it's treated as a non-parametric distribution, and at the end we have the model parameters that I wrote down here. So are the in the classical mixture model, the you have to deal with the means, but here the means are replaced by the speaker positions, and then because the video data, the visual data is in 3D, we have 3x3 covariance matrices, and for the auditory data we have scalar variances. So this is the parameter set that we have to determine. And then if you try to formally derive the maximum likelihood in the presence of the hidden variables, then you end up with this quadratic form. And what is interesting to remember here is that the two modalities, the auditory and the visual modalities are in fact linked by the fact that the two terms in this maximization problem, in fact, maybe I should use this. In the first term, you can see appearing here the function that maps, let's say, a speaker or a AV object onto the visual observation space, and here this function maps the same AV object onto the auditory observation space. So this are the Sn is the parameter that links the two terms in this expected complete data log likelihood. And there are other terms that are due essentially to the uniform distribution that can be omitted because they are constant with respect to the variable, to respect to the parameters that over which we take the maximization or the minimization. And then here the hidden variables disappear, but they are represented by their probabilities. So this alpha mn and alpha prime kn stand for the classical posterior probabilities of visual or auditory observation to belong to speaker n or to be an outlier. And now we have to take some distance with the classical EM algorithm, mainly because of this nonlinear functions f and g the effect of this nonlinearity is twofold. First, when you take the derivatives of these functions with respect to f and to s, then the maximization becomes a nonlinear problem, and it's not possible anymore to make this minimization over f and over g, as you notice that replace the cluster means with respect to the covariances. So we have to perform this minimization all at once over the entire parameter set. So although the E step is exactly the same, the M step becomes generalized EM, where in fact all the M step consists of one step of a nonlinear minimization, such like Newton-Raphson, for instance, and this replaces the closed form solution as in the standard EM. There are theoretical results that show that this GEM algorithm has the same convergence properties as EM, in the sense that it decreases the maximum likelihood, exactly like EM does. And so we basically the algorithm that we implemented starts by initializing the number of clusters and the cluster centers. So this is a very crucial issue, and currently we do not have a nice, elegant solution to the problem of initializing the number of clusters. We would like to consider a general case where people go in and go out. The number of AV objects changes over time in the scene, and we experimented with phase detector to initialize cluster centers, but it does a very bad job, in fact, because as soon as someone turns his head away from the camera, for instance, phase detection is not efficient anymore. So we are in the process of actually replacing this phase detector that initializes the algorithm with something that is more reliable, based, for instance, on optical flow, small changes in the images, etc. Yes, please.
In the objective function, could you explain what f is actually? How do you map the speaker location to the 3D locations of the stereo data?
Yes, in fact, I gave the, maybe I can come back to...
Because the points can be almost anywhere, right? The 3D points. So I'm just wondering, how do you actually map speaker location to the visual data that you actually obtain?
Okay, I understand. I think I understand the question, but basically this is the function f. The function f will map, will take position s, x, y, z, and it will project it in UVD space. Okay, so what your observations are in UVD space, what you would like to get is x, y, z. But there are many observations associated with the phase. Okay, so in our case, you will see there are interest points on the phase. So we assume that this should be clustered together, and at the end, the relevant information is the center of this cluster. Okay, so this is, and it's the assumption that this points are Gaussian is clearly not valid from a practical point of view. But this is the only probabilistic model that we yes.
Do you know in advance how many objects you have in the scene?
Yeah, this is exactly what I was talking about right now. In this case, yes, we start at time 0. We start with the phase detector. So this the phase detector basically we completely rely on it. So it says, okay, there are 3 phases, and then we take the center of this phase detectors as the cluster centers, and we say we have three phases, 3 clusters. Okay, but this is clearly not very good. Okay, yes.
So how does it handle the people that you said were outside the video?
You will see in a while. In fact, they are not AV objects.
So you have to have the video.
So they will be detected. You will see in a while. They will be they have an ITD associated as well as other noises in the room. You know, someone walking around, etc. And they are not. They are detected in the sense that the associated ITD is present, but then they will be treated as outliers. And as a matter of fact, it's a very interesting question, because you'll see another example when someone speaks while it talks, and while I do this, you concentrate on my voice, you have your auditory attention on me, but you don't hear my steps. Although the system will hear the steps, and you will see that it will be, in fact, in this second example here, I'll show in a while, there are 2 auditory sources. Okay.
How many microphones and how many cameras in this?
In all the examples I will show in a while, the setup, we have 2 cameras and 2 microphones. Okay.
You mentioned the first detector does a poor job, and it looks like you don't have any control. You don't do any tracking or association between.
Well, I'll show in a while. So maybe I just go through this, and then I will explain you exactly how. Yeah. Okay.
So the audio is not recorded with the dummy head, right?
Yes, the audio. What do you mean dummy head?
Dummy head, you find.
Yeah. It is. I will show in a while. Sorry, maybe I should have shown this in.
Because it's different. The function will be different with dummy head or without.
Yes, but this is carried out by the auditory part, exactly. And in fact, I forgot to mention, but this is done in collaboration with a speech and hearing group at the University of Sheffield.
Okay.
And they have taken care of this. So the ITD that we get, they have a different function. So we sometimes we use the dummy head, and sometimes also we have some recordings. We actually have 2 tiny microphones on someone's head. Okay, but of course they model this, and this is, I would say, done before that. So the way we treat the data is that we split each sequence. So a sequence is binocular binaural data. We split it into time intervals. So each interval is about 1/8 of a second. So this roughly corresponds to 3 video frames. And this is why so right now the phase detector runs in a static manner, but we plan to use these 3 frames within 1/8 of a second to actually detect some local motion and to rely more on this kind of features rather than on phase detection. And so roughly for each time interval, there are about 1,000 visual observations and 10 auditory observations, 10 ITDs. Okay, so there are 1,000 interest points in 3D and about 10 ITDs. Okay, so this is why I'm saying that visual observations are quite dense. There are many things out there, although the auditory observations are much more sparse. And so in this case, we take the 10 most prominent ITDs, although there are many reverberations, etc. So hopefully within these 10 ITDs, 3 of them correspond to the speakers. So this is the kind of result that we obtain. So let me just explain you a little bit. So it will be, I will show in a while the two sequences. And for instance, the first sequence, there are about 166 time intervals, out of which only 89 have AV information. Some of them have only visual information, etc. And we have been able to correctly detect 75 out of this 89. So here we have the percentage of missed AV objects, which is roughly 0.16. So I think these are percentages, if I remember well. I don't remember exactly. Good question. No, I think it's 0.16%.
89%.
Sorry. Yeah, it's 16%. Okay. And this is these are the false detections. So it's about 14%. Yeah, you're right. And in this case, as you will see in a while, is the working example. We have much more false alarms, about 43%. And I think, I don't remember exactly the reason, but it's basically because sometimes the person walks without speaking, and these are detected as AV objects. So this is so what I'm going to show here is a run of the EM algorithm. So this is how one time interval is processed. So what you'll see are the iterations of the EM algorithm. So what is marked with a white dot is the AV object being detected. So it's marked white on the right camera and blue on the left camera, sorry. So you notice that because of the presence of many interest points on the T-shirt here, this person, although we initialized it with a head, eventually the cluster center is on the T-shirt, not on the. So this is the situation in 3D. So these are the stereo data, and superimposed of the stereo data are the location of the 3 persons. And also the system is able to say speaking, non-speaking. So this is one example. So this is another example where only one person is speaking. In fact, the person, I think in this case, is the person in the middle who is speaking. And although it was initialized on the face, because the ITD in fact corresponds to the gaze, right? So eventually the position of the speaker is given by this, which is not necessarily let's say the mouth, the actual object that in fact is the acoustic source. Okay, so maybe I just interrupt the presentation to show you the same thing with sound. So the first part, in fact, goes. The first part of the video goes through the algorithm. So maybe I can just. So well, here you can see. Here you can see the one-dimensional auditory observations. So you'll see that so each bar here corresponds to an ITD. So here, for instance, there are 3 or 7, I don't know, 4 or 5 ITDs, or something like this.
Good English subject.
Yeah, not so bad today.
Not so bad here.
Yeah.
It could be what? Sorry, I interrupted. If we have a running day, maybe we will.
So here's someone else speaking, so there's nothing.
The draw. So
I know, yeah, this is quite good, I think. We don't have the reflection on the floor. And
Yeah.
it's quite, yeah.
So now we're going to check your perception. We're going to check how you perceive me moving from side to side, and how do you...
Okay, so this was the case where, in fact, there are 2 auditory sources, the voice and the steps, and the system tends to actually locate the person in the middle of the 2. Right? Yes?
So I guess you have a problem if 2 persons talking and walking at the same time. Clustering may get
well, this... Okay, so I think there was another question about whether we have a temporal model. So currently we do not have a temporal model. So what we do, we simply run an EM algorithm within a time interval about 1/8 of a second, and then we take the output of this algorithm to initialize the next step. Okay, so it's a very simple temporal model. We do not actually have, properly a temporal model. So what we show here is just our method running on a sequence. So to answer your question, I think currently we just take, the very short time intervals, and we process them in a sequence. So it should be able, I think, to detect 2 people working in the same time, provided that we have a good initialization at the beginning. So like, for instance, if I start with a phase detector that sees only 1 person and there is a second, then the system will think that there is only 1 AV object out there, and it will try to find only 1 AV object. So initialization is really, I think, a very important thing here. So we have worked on this. We started to work on this topic about 1.5 years ago. So these are the results that are currently available. So we discovered, in fact, that initialization it's very important. So I will just show you here. Oops. I will at the end I will show more about it. So now just let me go. Yes.
Steps thing. If you're just taking ITDs, the
yes.
steps actually there's no conflict between this pitch and these steps, right? They're coming from the same direction, so they're actually
yes.
helping, not hurting.
Yeah, there is a confusion because they correspond to the same ITD. Yes, the feet are not seen in the image. Okay.
Like this, or
No, like this. Like this, yeah. And then it means that the same ITD corresponds to 2 different AV objects.
So when you detect the person and the person is not talking, is just walking, you consider that as a failure?
Well, no. The system relies on initialization. So in this case, the system sees one phase. Okay, so it starts saying, okay, I have to detect only one cluster, which means I have to detect only one AV object. But so there are ITDs that correspond to the voice, ITDs that corresponds to the feet, and other ITDs. Okay.
The ITDs for the speech and the speech is going to be the same.
Yeah, they will be the same. So the system is unable to say that there are two AV objects.
The vision is different. So the vision tells them this is the same ITD when mouse talks. I think it gives a mouth observation. Then when it steps, it gives a step, the foot position. So then they average them. That's my understanding. So the same audio observation, same position from the audio sources, but a different vision.
He's not using the fact if the mouth is moving or not.
No.
No. It's not a mouth moving. No. Because they have feature points over here and feature points on the body for visual input. They have feature points over here on the mouth area.
What I'm saying is that acoustically speaking, if his steps were coming from his mouth, he could not tell the difference.
Right. Acoustically, they don't know. No. Acoustically, they have no idea. They don't know if the mouth is the food. It's the visual. It's the visual data.
Yeah. But the reason for which it puts it marks the person in the middle is because it's roughly the halfway in between the feet and the mouth. Okay.
I think it's just because of your features. You're getting features from the chart.
Yes, maybe a combination. Yeah, but well, I mean, you have an ITD. The ITD gives you a direction. Okay, but we initialize within this direction. We initialize the cluster center with a face. Although it seems to prefer to go down. I don't know why exactly, okay? But there is, if I have told the system at the initialization, hey, there are two auditory sources, or two AV objects out there, then it will anyway fail to find one of the objects because there's no visual data associated with it. Anyway, so now I will show a little bit how the data were gathered. And one point here was to record this AV data from the perspective of an active speaker. And the data set that that is available on this website is described in a paper that will appear soon in ICMI this year. And we also provide associated software for audio feature extraction, video feature extraction, and also maybe in the future we'll also put on the site the audiovisual fusion algorithm. So I don't know if this, but basically this is the setup. So this is the dummy head that, so it has two microphones, and we have a helmet on which we put the two cameras, and so this can go on some. So there are two possibilities. Either we use this dummy head, or we can put the helmet on someone's head, a physical person, which in this case will wear the microphones in the ears. And this device here is in fact associated with this camera, and it will provide 6 degrees of freedom motion of the head. So we have stereo pairs at 20 frames per second, binaural auditory at 44.1 kilohertz, and the head position and orientation at 20 frames per second as well. These cameras and this camera are perfectly synchronized. And this is the general view of the system. So we use. By that time, we had to, because the auditory software was running on a Windows computer and our software ran on a Linux computer, we had difficulties to synchronize through NTP all the computers. So we simply, for audiovisual synchronization, we systematically introduced the clap. So, but I think now we were able to get around this problem and synchronize all the computers such that we have synchronized data. Okay, so I'm done with the first talk. And the method that does audiovisual fusion in the 3D domain is based on unsupervised clustering using the GEM algorithm. And we actually plan to extend this to deal with a varying number of AV objects, which means that the number of AV objects can vary over time, people coming in, coming out, and not only people, but other kind of AV objects. And the reason for which we chose to use a binocular binaural setup is because it allows very strong links with neurophysiology. In this project, we have neurophysiologists who study audiovisual attention, which is in fact quite new field in neurophysiology, to study binocular and binaural perception within the framework of attention. And a more sophisticated model should include eye and head motions, which are, in fact, I don't have a photograph here, but we've built a robotic head that, in fact, has eye movements, binocular eye movements, and active perception and attention will be studied within this framework. So this is the reason for which we chose to use binocular binaural setup. So I'm done with the first talk. See if we have more questions on this. Yes, please.
I was just wondering if you could talk a little bit about the application you see for this.
Yeah. So what the application that we'll target here is a robot human interaction application. So we'd like to mount such a audiovisual head onto a robot. So we have a collaboration with a robotics company in Paris, in France, that is very interested to. It's a small humanoid robot, and they are very interested to study the social interactions of this tiny robot with people. So the first task that the robot will have to do is to be able to distinguish between, let's say, people versus other things in the room. From the visual point of view, it's very difficult, and so we thought that combining audio and visual would be a nice way to be able to distinguish between, let's say, living objects against artifacts. So this is maybe one of the motivations for doing this kind of work. Also, we have a more theoretical motivation because we noticed that audiovisual integration. I'm from a computer vision background, and Zhengyu just told me that when he started to do audio, he thought it was easy, but in fact it's not easy at all. And in fact, in some respect, auditory people have discovered the probabilistic and setup much earlier than the computer vision people did. So, so somehow they neglected some other things, like the simple physical geometric facts about auditory perception. So when we started this and we tried to put this together, we wanted to emphasize these things. Okay. Yes.
I'm just kind of curious about the GM algorithm. So does this system heavily depend on the initialization? I mean, for example, for usual EM algorithm, the first initialization is really important because you can get local minimum whatever. But the case here is that, well, I'm just curious. So, for example, one phase is detected wrong, so you guess this algorithm still robust enough, can correct.
When we talk about initialization, there are two things. One problem is, in fact, with let's say with GMM models is the number of the number of components. So the number of components. So this is one initialization issue. The other initialization issue is where are the which are the means and covariances of the components, the initial values. So we started to address the number of components. In fact, we use the big criterion to determine the number of components based just on the auditory sources. And in fact, we have very nice results there. Although we have to run this over a short period of time, like 1 or 2 seconds to determine. So, but of course, this will give you the number of auditory sources, and then over time, the number of auditory sources may change. Okay, someone else comes in, etc. So, it's not, I think, just a question of initialization, as you say. I think it's a much more general issue. Then how do you allow such a system to all of a sudden to say to the small robots, hey, some new person that I haven't heard for the last 5 minutes coming in the room. Okay, so this new piece of new observations, how do you take them into account? So I think it goes beyond. It's a much more difficult problem than just saying that it's properly initializing EM. It's more general. Yes.
My concern is about actually in audio, when you have multiple sources, it's really difficult to, when they are overlapping, it's very difficult to localize them, for example, or even to do whatever processing. Here, I was surprised to see that with 2 microphones only, we were able to localize 2 speakers who are active at the same time. So maybe they are using kind of speech cues which are sparseness or something.
We just detect as many ITDs that there are possible out there. And then because we know in advance that, in this case, we know in advance that we have to look for 3 speakers. Okay, because we have a phase detector at the start. We know that we want, I should not call them speakers because there are 5 speakers. Okay, I prefer to call them AV objects. So we know that there are 3 AV objects out there. Okay, so then the unsupervised clustering technique that I described will consider 4 clusters, possibly 3 for AV objects and 1 for outliers. And it turns out that the 4th component is very important for what you're talking about. And the fact that the visual observations are systematically associated with the auditory observations through a generative model that I showed you, which is the exact physics of the problem. I think it's very important, which in fact leads to a generalized EM algorithm, but it does a very good job in detecting simultaneously several AV objects. Okay, so I can send you a paper if you are interested. If you send me an email, I can send you a paper that describes this in detail. Okay, so so now I'll switch to the other talk. Okay, so let's see. I don't know what is the resolution. Yeah, okay. Maybe I should start with the. Okay. So although it's a completely different application, it will boil down to EM as well. A very different instance of EM, but anyway, it will boil down to EM as well. So, so what I'm going to present here was in fact presented at CVPR 2 weeks ago in Anchorage. So the title of the talk matches exactly the title of the CVPR paper. So what we want to do here, we have 2 objects, 2 articulated objects. So in this case, for instance, we have a small wooden mannequin and the person. So this, I'm showing the images of this, but in fact what we have are voxel data that are gathered with a multiple camera system. So what you see here is the voxel data for the first object and the voxel data for the second object. And the output of the algorithm is the dense matching one-to-one between all the voxels in the first set to all the voxels in the second set. So this is the output of the algorithm. And okay, so why are we interested in shape matching? It turns out that is a fundamental problem in computer vision. How do you not only how do you describe shape, but how do you compare shapes? And it's also useful for object recognition and indexing, motion capture, gesture actor recognition, also links with computer graphics, for instance, where people are interested into shape morphing and texture morphing so that they get around classical motion capture techniques. So all these topics are relevant to all these applications and problems are relevant to the problem at hand, which is shape matching. And the methodology that I'm going to present, so this is much shorter than what I did the present talk, so because I was supposed to give 2 short talks. So the method that we've implemented goes as follows. So we have, as I said, 2 3D shapes that are represented by voxels in this work, but in fact we extended it to meshes. And it can be also 2D shapes, for instance, represented by clouds of points or by silhouettes or whatever you like. And then because each shape is described not only by the positions of the point sets, but also by the local geometry and the topology of these points, then in our case, the 3D shape is strictly identical to a sparse graph representation. And therefore, shape matching becomes a problem of graph matching. And we will use spectral graph theory and the Laplacian embedding to represent such graphs into an isometric space. So this is the key methodology that we've developed. And then once we do this, what is interesting is that the shape matching, so we start with 2 articulated shapes. So there is no possible, so these 2 shapes, they do not correspond in terms of, there is no transformation that maps one shape onto another. So, but because of this piece of methodology, then the shape articulated shape matching becomes a point registration problem. More precisely, it becomes a rigid point registration problem. Although it is not a classical in the classical sense, in the sense that the shapes are not projected onto a 2D or a 3D space, but a higher dimensional space, and the dimensionality of the space corresponds roughly to the complexity of the shape. And then this rigid point registration problem will be solved in a probabilistic framework within maximum likelihood with missing data. So you can look at the CVPR paper if you want more details. So okay, so just the central idea of the method is to embed a sparse graph into an isometric space. So so basically this is a graph that I'm representing here, and the nodes of this graph will become points into a space that is spanned by the eigenvectors of a matrix associated with the graph. In the classical spectral graph matching, the matrix that represents the graph currently is the adjacency matrix. So there are a number of people who actually addressed the graph matching problem by looking for a permutation matrix between the two graphs. So this writes analytically like the expression on the top, where okay, I lost my. I don't know what maybe. Yeah. Okay. So let's say that the two graphs are represented by matrix matrix A and matrix B. So P is a permutation that takes one matrix and maps it onto the other. And then the problem is to find P that minimizes the Frobenius norm in between these two matrices. And the spectral graph matching is a very nice method that, at my knowledge, was introduced by Umeyama. I think it's in this paper, I think it's a 1988 paper. So it's 20 years old. That he showed that if the eigenvalues of the adjacency matrices are distinct and if they can be ordered, which is a very strong assumption, distinct and can be ordered, then the problem becomes a point matching problem as opposed to a matrix, let's say, alignment problem here. And then the nodes in the two graphs are x, y for the first graph and y, y for the other graph. And then, in fact, if you are able to order the eigenvalues, then there is the matching problem has been solved. Because there are as many eigenvalues and eigenvectors as there are, in fact, nodes in the graph. And then all you have to look is to look for a orthogonal matrix that maps that aligns the two clouds of points. So it is, let's say, on paper the problem is solved like this. I should also mention that there are other problems due to the fact that when you compute the eigenvectors, there is a sign ambiguity. So in practice, it's not that simple. So the problem boils down to a Hungarian algorithm, which is bipartite matching problem. And it has n cube complexity, where n is the number of nodes. So, okay, maybe. Yeah, sorry. Yeah, are the nodes in the graph become points in an Euclidean space. So these are x1, x2 for one graph. Okay. Okay. So now, for various reasons that I wouldn't detail here, one has to use the Laplacian matrix rather than the adjacency matrix, which is a much richer description of the local geometry, local topology of the graph. So this is how this Laplacian matrix is built. So an element of this matrix, first of all, let's define Wij, that basically if node I belongs to a neighborhood of node J, then you can write the distance, geometric distance, for instance, between, or Euclidean distance between I and J, and then you take the Gaussian kernel over this distance, divided by some parameter that you have to specify. So this actually, and zero otherwise. So this clearly, it's a very local, it's a local, it acts only locally on the point set. And then the diagonal terms are computed like this. It's a sum over a line over a column doesn't matter because the matrix is symmetric. And then from this you can build a Laplacian matrix. And so another important point here is that rather than taking all the eigenvalues, therefore all the eigenvalues, you can just skip the first one, and then you can take the first k eigenvalues, and then give you so k is the dimension of the space in which you are going to project the graph. So there's no reason for k to be 2 or 3. Okay, can be any number. And then the problem is to are these, let's say, k smallest eigenvalues of the Laplacian matrix, are they distinct? And if they are distinct, can they be ordered? And this is just an example of a voxel set here that contains about 20,000 voxels. So there are 20,000 eigenvalues and 20,000 eigenvectors. So this is the shape in, let's say, projected onto a k-dimensional space. And what we show here are actually the values of the eigenvalues. And you can see that here, of course, this is also flattened by the resolution. But you can see that the first 10 or 20 eigenvalues are, you have to go to the fifth significant digit after the comma to rank them. And they are analyzing the geometric and algebraic multiplicity of this kind of thing. Maybe a topic in its own right, but we didn't want to do this. So the question is, how do you go around this problem? Because now you cannot apply the classical spectral graph theory because the eigenvalues cannot be ordered anymore. Okay, so if you have a way, okay, so why is it important? Why it's important to order them is because the ordering of the eigenvalues and eigenvalues will give you an order onto the eigenvectors here. So, okay, so on one side you have x, y, z, let's say, and if on the other side you have y, x, z, then it is not possible to compare the two shapes, okay, because the transformation is not isometric. So this is why it's important to yes.
The eigenvalue is essentially 0.
In theory, sorry. The smallest eigenvalue is 0. Okay, so you have to skip this, and then the other eigenvalues are not 0. But in practice, they are very small. Okay.
So what's the D? I forgot.
D is this matrix.
Oh, D is this one. Sorry.
Yeah. W is this matrix, and D is this matrix. Okay? And then you take the eigenvalues and eigenvectors of a matrix L.
So then the Dij is really the Euclidean distance?
You can take any distance. You can take the Euclid.
D is a diagonal matrix.
No, yeah, sorry, there is a confusion between the notation. This and this are two different things.
Right.
Sorry.
Yeah. So Dij on top, I assume you just use Euclidean distance.
You can use Euclidean distance, but you can use any distance. You can use the geodesic distance, you can use Manhattan distance on a, for instance, voxels are regularly spaced, right? So you can use the Manhattan distance, you can use any distance. You can use the Norman distance.
No, because eventually
you can use a path, right, between two voxels. Shortest path between two voxels.
Your eigenvalues, the distribution of your eigenvalues will depend on how you define the distance. Right? That's very.
Maybe yeah. As I told you, sure, maybe yeah.
I assume that, for example, I think if you just simply use Euclidean distance, you don't weigh anything. Then you should be just three. You should be embedded to 3 dimensions because that's x, y, z. if everything just would be distance?
Well, in fact, with this representation, you start with, intuitively you may think that each node has a location in space, x, y, z. But in fact, we do not use this. We use the relative distance between node pairs. Okay, so what the Laplacian matrix contains is not the x, y, z coordinates of the point, but these distances as the okay. The Laplacian matrix tells you location, the position ij in the Laplacian matrix tells you what is the distance between node I and node j according to this definition.
Define the neighborhood if I is in the neighborhood of j or something. Area to see the.
In the case of the voxels, I think we use the voxels. It is the equivalent. It's a 27 neighborhood, right? 20 or no? 26 neighborhood, right? In terms of voxels, right? It's like a 9. It will be like an 8 neighborhood in 2D.
So if you increase the neighborhood or shrink the neighborhood, it has some effects on the.
Of course, yes, of course, yes. The reason for it is that when you'd like to be invariant to this kind of motion, right? So when you have this position and then this position, ideally you would like to have the same graph representation. And there's a compromise between. It's a compromise. The side of the neighborhood here is one parameter, and then also the size of the kernel is another parameter. Okay. It turns out that, but I.
So it's an exponential function with fit.
Yes. Yeah. Anyway, did I answer your questions? Okay. So the key innovation here, as opposed to these ideas, is to do the ordering of the eigen so what we want to do, we want to order. Let's say that we have two graphs. So these two graphs will be represented by two sets of eigenvectors. So we'd like to order them in the same order. Okay, say 1, 2, 3, match 1, 2, 3. Okay. So again, the details are in the paper, but we noticed that so what is called here the eigenfunction is in fact an eigenvector. So so if you consider the histograms of the eigenvectors, it is very easy to figure out that the histogram is invariant to the order in which you consider the eigenvectors. So we simply notice that the histograms of eigenfunctions, eigenvectors, are a very reliable signature of the eigenspace. And therefore, what I'm showing here on the left side are the some eigenfunctions, the histogram of some eigenvectors associated with the first shape, and this is associated with the second shape, and I'm showing them ordered by the eigenvalue. So you may notice that although the first two eigenvalues introduce the correct ordering, here there's a problem because, in fact, this one should match this one, and this one should match this one. Also noticed here that this histogram is reversed, is the negative of this histogram, and this is simply due to the fact that when you compute an eigenvector, you don't know if you should take the eigenvector of the negative of the eigenvector. So by actually comparing these histograms, and then you can simply find a one-to-one mapping between the eigenvectors in the first graph and the eigenvectors in the second graph, and maybe disregard some of the, like for instance, this guy is disregarded and this guy is disregarded.
So each row represents one eigenvector.
This is the histogram of an eigenvector. Okay, so there are an eigenvector has, so like for instance in a graph you have 20,000 voxels. Yeah. So an eigenvector has 20,000 components, right? So
what the vertical axis is like the bins, like you divide it into bins. Like
sorry?
What's the vertical axis? Sorry, horizontal axis.
This is a histogram.
But what the 200 means? 200 what? 200.
The component? Value of the component?
Yeah, this. Sorry. Yeah, these are the components because
you have 20,000 components, right?
I think simply. Hold on. No. These are the number of components. It's a histogram, so these are the number of components that give this value, the number of components, this value, etc.
200,
so, like for instance, here it means that there are 125 components that give this value. Sum up to this value.
Consider the eigenvector as a data set, and then you plot the histogram of this data set.
Okay, so the vertical axis, the vertical one to 1,000, that's the
value of
that's
the
that's the value.
Yeah.
But the vertical one, the horizontal one is the count.
Yeah.
Okay. Because sometimes people do the other way around.
Yeah. Well. Okay.
The range of the small eigenvalues, how do you know it's related to motion, not related to noise or errors?
No, that's a good question. What we do, we take, at some point you have to, again, you have to start with something, okay? You have 20,000 eigenvalues, so we take the 20 smallest ones. And we assume that our eigenspace that we want to analyze is within this 20-dimensional space. Then we take all the eigenvectors. So there will be 20 eigenvectors on one side, 20 eigenvectors on the other side. We start by ordering them with the eigenvalues, and then we compute the histograms, and then we match. We compute the distance between the histograms, and then we match them. So this is an algorithm that is in n power 3. Okay, so for 20, it's not that expensive. It's quite fast, in fact. And then it will give you the number of histograms that match. And then we put a threshold on the quality of the histogram. So this will give you the final dimension. So in fact, in this case, in the example I'm showing you, the dimension is 5. The dimension that was chosen is 5. But I agree that this is quite ad hoc, and we are trying to figure out how to do this analysis in a more systematic way. If you are on the theoretical side, you like to understand the properties of of matrices of very large size with a multiplicity of eigenvalues and eigenvectors, etc. There are algorithms that give you the exact characteristic polynomial, for instance, of a very large matrix, and then factorizing this polynomial to find the multiplicity of eigenvalues can take a week of computation. So it's a very expensive, very costly. So we decided to skip all this theoretical part and do something that is more pragmatic. But I agree that there are some problems.
It also depends on the degrees of motion and what's your
Well, we do not have any motion here. We just take one position and then another position. No. You take one position and then another position, and you try to match them. Okay. So now that so we did two things. We reduced the dimensionality of the problem, but also we aligned the two eigen bases. So now the eigenfunction alignment chooses the dimension k of the embeddings. So we are in the range 6 to 10, in fact 5 in this example. And however, now we have two sets of points that have different cardinality. There is no reason for which the two voxel sets should have the exactly the same number of points. And there will be, because there are so many, there will be multiple matches, missing shape parts. For instance, if in one position I'm like this, and the other position I'm like this, you know, in fact, this shape will be missing from one data set. And there is noise, outliers, etc. So we have to handle. So now that we have a way to, let's say, to choose the embeddings and choose the dimensionality and have an initial alignment of the eigenbases. However, we are still left with the problem of solving this problem of multiple matching, missing shape parts, etc. So this is why now we are dealing with a point registration problem. And okay, I'm going to skip this. And again, we are in the framework of maximum likelihood. And more specifically, because the maximum likelihood, because of the presence of the missing data, we cannot directly solve the maximum likelihood problem. And then here, the missing data are the assignments between the two voxel sets. And just show you how the system is supposed to do. So let's say that we have two sets of points. So the first thing that we do, we apply an k by k isometric mapping. So in this case, will be a rotation, k by k rotation. So it will be a orthogonal matrix with a determinant equal to 1 to the first set. So then this set becomes transformed and it is overlapped on the second set. And then we have each point in the second set is the mean and of a cluster. And then we have covariance that represents the size of the cluster and the shape of the cluster. And then we have to decide whether the points from the first set are inliers or outliers. Sometimes there are multiple matches and also empty classes or empty clusters. So these are the kind of things that we want to solve. And so we put this into a framework of this robust point matching problem. We put it in the framework of density estimation. So we treat the 2 points, unlike many techniques in point registration, we treat the two sets in a non-symmetric way. So one point set, let's say in general, the largest one corresponds to an observation set, the other one to cluster centers. And then the problem is to group n observations into m clusters. And also, as in the previous talk, we have to choose a distribution for the noise component in the mixture. And some people add a Gaussian component as an outlier cluster, which is not really efficient from a practical point of view. I don't want to go into the details here. Other people don't add an outlier component, but they simply use a mixture of t distributions because it has the reputation to be more robust to outliers. And we decided, as in the previous talk, to add a uniform component to the mixture. And therefore, I don't want to go into detail, but this is exactly the same kind of modeling and goes to the same kind of formulation. So the point registration now becomes an EN algorithm where we initialize the transformation Q and the covariance sigma. So just here, just to mention, because of the eigenfunction alignment that we did before, this is initialized to the identity matrix. And I will show you the results. It does a very nice initial alignment. Then all you have to initialize are the covariances. So you can take them very large. And then the E step computes the posterior probability. And then the M step estimates the transformation. And then the covariance. So this is I don't want to go into detail, but this is an important difference with the classical EM, because you cannot compute the transformations independently of the covariance. So it is formally it is not EM, it's ECM, expectation conditional maximization, because the transformation Q, the maximization of Q is conditioned by the current knowledge of the covariances, and etc. So just to show you an example, oops. Okay. So so this is a simulation. So the blue dots are the cluster centers. The green dots are the observations, and the red dots are outliers. So you may notice that sometimes, so this is a random initialization. You'll notice that sometimes the outliers are much closer to a cluster center than the inlier, etc. So so what I will show you now is the evolution of the EM algorithm in this case. So at the end, okay. So this in this example, the inliers are not corrupted by any noise. So this is why we obtain a perfect match. And you notice that all the outliers were disregarded, although in some cases they are very close to the inliers. And there are approximately 15 inliers and 10 outliers. It's just and the outliers went to a uniform component of the Gaussian of the mixture model. And we tried this with lots of cases, lots of noise, etc. It works very nicely. So now this has to be applied to our problem. So this is the video that shows the technique. So this is 6 images of the object in one position, and then these are 6 images of the same object in a different position. So in one position the hands are like this, and the other one they touch each other. So there is a topological difference in the shape. And one reason for which we wanted to show this example is to show how such an algorithm handles these topological changes. So this is the voxel reconstruction of the first shape. And this is the voxel reconstruction of the second one. And these are the embeddings. So on the left, we show the eigenfunctions that correspond to various eigenvectors in the embeddings. So sometimes the embeddings have a very weird shape. So this is the, this is the initial, maybe, I don't know, maybe I stop it too. Sorry. Maybe I should go back. Yeah, so this is the alignment as provided by the eigenfunction alignment that I showed you. So the EM algorithm starts here. So So these are the various projection in a three-dimensional space. So this is the results shown independently, so that because otherwise it's difficult to see the with a dense matching like this, it's very difficult to see. But believe me that the matchings are correct. You can see that this goes. The colors help you a lot. This leg goes to this leg. They are crossed, etc. Okay. So this is a nice example with a hand where in one hand is open and the other one finger is bent, I think, and it touches the other one. So this is the example that I showed you at the beginning with two different objects, artifact and a person. So this is a sequence where when someone actually runs, and there is no, again, we don't need any temporal model because it can handle topological changes and very different articulated poses of the same shape. So it doesn't actually need any initialization or any temporal. In fact, this method doesn't need any initialization. Okay, so 5 minutes
really
too late anyway. So the method that we propose embeds the articulated shapes in a k-dimensional Euclidean space. And what is nice here is that k is not chosen in advance. It depends on the complexity of the shape. And typically for people, the dimension is of the order of 5, 6. And matching consists in two steps: aligning the two k-dimensional eigenbases based on the histograms that I showed you, and then finding the optimal transformation that aligns the largest subsets of points in between the two sets, which in fact boils down to a rigid point registration problem. And it handles missing shape parts, noisy data, bad points. They explicitly take into account, and we carefully designed the uniform component and the associated EM algorithm to handle this kind of situations. And I just want to mention that the dimensionality remains a problem, because if you have very complex shapes and then you want to have k equal to 10 or to 15 or something like this, then computing the covariance matrices of in dimension 15 and computing the I don't know if you're familiar with EM, but at some point you have to compute the determinants of these matrices, and you in dimension 15 you have to you use a power 15 over 2 or something like this, right, in the covariances. So it can be a problem. It can be a problem, of a numerical problem. So we in all the examples that I showed you, we use a spherical covariance. And if you want to use a non-spherical covariance, the EM, it's much more complex because you run into a non-convex optimization problem if you use, I don't know if you know the classical algorithms that align point sets using, in 3D for instance, they use quaternions. In k-dimensional space, it's not, quaternion representation is not possible anymore. Plus, because of the presence of the Mahalanobis distance instead of the Euclidean distance, then you end up with a non-convex optimization problem. So then it becomes, so it's not that simple to go from spherical covariances to non-isotropic covariances. So, okay. So,
thank you very much.
Okay, just to mention that I have a demo, so if you are interested to see this working on my computer, I can show you. Okay.
Thank you.
Okay.